Hey guys, this is our video for the lesson 9 group problems, and we're just going to get started with number 1. So number 1 asks us to diagram an intermediate stage of DNA replication in E. coli. Draw 2 replication forks proceeding from a single ORIC, the origin of replication. It may be easier to draw a linear molecule. Okay, so we're just going to draw it. So starting from the ORIC, there are a couple of things that are going to happen. First thing, we don't really care about order, just in terms of our picture. DNA primase is going to lay down an RNA primer right here for our leading strand going in 3' direction, and then primase is also going to be putting down these little RNA primers for our leading strand over here, for our Okazaki fragments on both of the lagging strands. I didn't draw them right here, but I'll get to that in a second. DNA helicase is pictured here in red on both sides, and that serves to kind of unzip our DNA. Our replication fork is going this way, and there's another going the opposite direction. Now my RNA primers I showed in green, as I mentioned before. We need just the one RNA primer to start our leading strand on both sides, and for synthesizing an Okazaki fragment, we're going to have a little RNA primer at the start of each individual fragment. So that's why there's 3 over here shown in green. My leading strands I've pointed to a couple of times. I've labeled it right here, and it's going to continue replication going that direction. Up here, this blue is going to be my leading strand. DNA polymerase 1 I drew over here in blue, kind of that bluish circle, and picture with me kind of what the DNA polymerase 1 is going to do. Originally, there was an RNA primer here for the Okazaki fragments on this lagging strand. DNA polymerase is going to come in with its exonuclease activity, get rid of those guys, and we'll remove those RNA bases and then replace them and fill in that gap with the appropriate DNA bases. The DNA polymerase 3 alpha subunit is shown in black on both of my leading strands, and that is going to be the machine that adds nucleotides to the leading strand. Very high processivity. It'll add a lot of nucleotides before it dissociates. The last thing that number 1 asks us to draw were these Okazaki fragments, which again correspond to the gaps in these RNA primers, also shown in blue. So we've got 3 right here, and 2 Okazaki fragments up here, which then DNA polymerase filled in the gap between those. So hopefully that made sense. There's a little picture of DNA replication for number 1. Number 2 is asking us to fill in the blanks and indicate the correct protein that fits the description. So for question A, this protein complex synthesizes primers in eukaryotes. Well, that should be the DNA primase and the DNA polymerase alpha complex. So the primase and the alpha complex. Question B asks us which protein, this protein promotes the separation of AT-rich sequences within the ORIC. That would be DNA A. Question C says this subunit of DNA polymerase 3 contains proofreading activity. That would be the epsilon subunit of DNA polymerase 3. Question D asks us, or says, this protein synthesizes the leading strand in eukaryotes. Well, that would also be DNA polymerase epsilon subunit. Question E says this protein displaces DNA polymerase 3 from the chromosome to terminate replication. That is going to be the TUS protein, TUS. And we are going to pass the time over to Rochelle to finish up number 2 for us.
For question 2, letter F, the protein has 5' to 3' polymerase and 5' to 3' exonuclease activity. The answer would be DNA polymerase 1. For G, this protein introduces negative supercoils into the DNA ahead of the replication fork. That would be DNA gyrase. For H, this protein binds directly to the ARS elements. That would be ORC. For I, the protein prevents DNA strands from annealing during replication. That would be your SSBs. And for J, this enzyme seals the Okazaki fragments into a continuous strand of DNA. That would be DNA ligase. Moving on to question 3. This question concerns the enzymes involved in DNA replication. For A, the 5 enzymes that consume ATP during DNA replication will be DNA A, DNA helicase, DNA gyrase, DNA primase, DNA ligase. For B, the 5 enzymes that consume DATP during DNA replication will be DNA polymerase 3, DNA polymerase 1, polymerase delta, and polymerase epsilon. For C, the 5 enzymes that have 3' to 5' exonuclease activity, that will be DNA polymerase 3 and DNA polymerase 1. For D, the 1 enzyme involved in replication that uses DNA as a template to synthesize RNA will be a DNA primase. And then for E, the 1 enzyme that uses RNA as a template to synthesize DNA will be a telomerase. Telomerase? Okay, so we'll turn it over to Tanner.
I'm going to begin by drawing our template DNA backwards from what it has in the problem. So I'll draw 3' to 5'. It'll help us solve these problems. We barely made it. All right, so for each of these situations, we're going to have the same primer. So I'll draw that in 5' to 3'. It will go like this. And you'll notice it matches the ATCG rule perfectly up to this point. Now, for each situation, we're going to be adding a different mixture of nucleotides, and we'll see how far we can get in synthesis before we run into the problem. For A, we'll be able to go all the way because we're given just the normal deoxy triphosphate nucleotides. So to draw this out, it'll look something like this. So for number A, our first product will be this line. We'll go A, C, T, G, A, T, G, C, T, C, C, T, G, C, T, A, T. For number B, we have the same mix of nucleotides with the exception of our C is only monophosphate instead of a triphosphate. So we're going to run into a problem there because without the phosphate bonds, we won't be able to attach the C onto our line. So for B, we're only going to get as far as the first nucleotide, and then we won't be able to attach that first C. So our string will just be a little 5' A, 3'. That's it. For C, we have an RNA. So instead of T, we have a U. That's going to be a problem because we can't mix RNA and DNA. So we'll only make it the first 2 bases before we run into a problem here. So we'll just have a little strip that's barely long to be 2 nucleotides long, AC. For D, we have an RNAG. It's we just have a normal guanosine triphosphate, so the deoxy guanosine triphosphate. So we'll only be able to get 3 nucleotides before we run into a problem. It would be A, C, T. And that would be for number D. For problem number 5, which of the above proteins is found in prokaryotes? Prokaryotes have DNA gyrase, TUS, DNA A, DNA polymerase 1, DNA polymerase 3 alpha subunit, and the DNA primase. For B, which of the above proteins is found in the mouse? Mouse is just eukaryotic, so we'll have CDC6, DNA polymerase epsilon at alpha, DNase primase, MCM helicase, telomerase, and pCNA. C, which of the above proteins is involved in chromosome compaction? None of these are. However, we did talk about topoisomerase or DNA gyrase. Actually, DNA gyrase, excuse me, which is also called topoisomerase, is actually involved in chromosome compaction. Which of the above proteins is involved in the initiation stage of DNA replication? That's CDC6, DNA A, and MCM helicase. Then for E, which of the above proteins is involved in the termination stage of DNA replication? That's the TUS. So thanks for watching and have a good week.